Hello, welcome to lesson 9.7. Today we're going to be talking about dilations. Now keep in mind dilations will keep the shape of your figure the same, it's just going to change the size. So careful when graphing that or constructing that out. Let's go ahead and take a look at the notes so we can see what we will be working with. All right. Okay, so today we want to be able to do three things with our dilations. First, we want to be able to calculate the coordinates of dilation. We also want to determine if our dilation is going to be an enlargement or reduction. And we want to be able to construct that or look at that on the graph. Go ahead and make this bigger. There we go. So we can see. Okay, so a couple of things to keep in mind. The transformations that we have looked at so far are your translations, reflections, and rotations. Okay, each of these is what we consider to be a rigid motion. Okay, the shape has to stay the exact same size. It has to stay congruent between its pre-image and image. That does not occur with a dilation. Okay, if you do have a dilation, and I want you to think about like when your eye dilates, okay, it gets larger, and then once the drops wear off at the eye doctor, then it gets smaller, okay, but it's still in that circular shape, okay, it's just enlarging and reducing. Okay, your dilation on your graph is going to work the exact same way. So in your dilation, a transformation will enlarge or reduce the figure, but the result has to be similar to its original. Okay, so here's some new vocabulary here. When you think of similar, you want to think exact same shape, it's just a different size. And we'll kind of analyze that on our graphs. So we think of how it's going to enlarge and reduce by its scale factor. Okay, think of blueprints are usually drawn to scale. Okay, they just look smaller than the actual building. Okay, they are scaled appropriately so that those measures can be calculated. Okay, so scale factors are very important. When we calculate what the scale factor is actually going to be, we measure it from a center point to the image, okay, over the center point to its original location. Okay, if your image is further away from the center, that means it's moving further away. It's getting bigger and bigger. It's going to be an enlargement. If your image point moves closer to the center point, okay, it's going to have to make the shape smaller to get closer, so then that would be a reduction. When your numerator is larger than your denominator, okay, it's going to have a value greater than 1. If your numerator is less than your denominator, okay, that's going to give you a dilation smaller than 1 and be a reduction. Now, what I want you to recognize are a couple things here. First of all, okay, C is considered to be the center of our dilation. Okay, that's the center point, the point at which we're measuring the dilation from. Okay, in this case then, I see my image right here. So this is my original figure. Okay, I can tell that because it's marked with just a P. We then applied a dilation, and you can see that your shape is now larger, okay, and it moved further away from that center point. I know it is the image because it's marked as P prime. Now what you're also going to notice is that those vertices that correspond, like P and P prime, they have to stay in line with your center point. So a lot of times you see it drawn on the construction, how it lines up with the center. All right, so if I move down here, okay, to the very bottom, okay, to be looking at this picture of a dilation itself. The first thing that we want to analyze with this is this going to be a reduction or an enlargement? Well, identify a point that's on the original figure and compare it to its corresponding point on the image. So here I can see P would be my original. P prime represents my image. Okay, I should see that where we have our prime notation, this is a smaller figure. So this is going to represent a reduction. Okay, so always look carefully to determine if you have that enlargement or reduction. Okay, so if we're going to look at number 2 here, okay, find now the scale factor of our dilations. We're going to go back to what that formula was. We use K as our variable for a scale factor, and that formula was C to P prime over C to P. So I analyze where my center point is on my figure, and which is my pre-image point and which one's my image point. Okay, in this case, if I go from the center to my image, okay, center to my image, that's marked right here as 14 units. Then my center to my pre-image right here, that is only 6 units. If I go to reduce this, I get a scale factor of 7/3. Okay, 7/3 is a value larger than 1. Therefore, this should represent an enlargement. And if I look at that, my image where P prime is located, this right triangle is larger than this right triangle here. But you should see that they are similar. The triangles look like they are the same shape. They're just a different size. All right, in number 3, okay, we are told that you are projecting images onto a wall with a flashlight. The lamp of the flashlight is 10 centimeters away from the wall. The pre-image is imprinted onto a clear cap that fits over the edge of the flashlight. The lamp of the flashlight is located 2.5 centimeters from the pre-image. Okay, so in this case here, okay, if we were looking at this, okay, here's where our lamp is located. Okay, you can see that the original X right here on your flashlight is your pre-image, that's where it starts, and then its reflection that it creates is out here. So again, this is going to be considered an enlargement. And if I looked at finding that scale factor, okay, my image ends up being 10 centimeters away over the original, which was 2.5 centimeters away. Now, a fraction is just division, so 10 divided by 2.5, okay, gives us a scale factor of 4. Okay, again, larger than 1, so this does represent an enlargement. All right, now in our next problem, we're now going to work with placing those dilations on our graph. Now, as we begin to look at these coordinates, okay, we want to understand that when we're on the graph, we're going to take the origin, okay, as our center of dilation here at the beginning. It doesn't have to be located at the origin, but that's the standard place on the graph. They don't tell you something different. Okay, and then here's the coordinates we would have here if we looked at number 2, since this one's set up for us. Okay, graph the image of parallelogram WXYZ after a dilation with a scale factor of 2. Okay, well, what I want to do is take what the original coordinates of each of your vertices was and multiply it by our scale factor to get where our image points would move to. So W is located at 2, -3. So W prime, or the image, would then have to move twice the distance from the center. So 2 times 2 would be 4, and 2 times -3 would be -6. So now I'm going to move W prime to 4, -6. So that's going to place W prime, okay, in that location. Okay, if I look at my next point here, I'm just going to go to Z. Okay, Z is located at 5, -3. Therefore, Z prime would then need to be multiplied by that scale factor. So 2 times 5 would give us 10, and then 2 times -3 would be -6. So I would go to 10, -6, and that would place Z prime in that location. All right, point X. X was located at 1, -5. That would place X prime located at 2, -10. So 2, -10 would be located here. So there's X prime. And then my last one, which was V. V originally was at 4, -5. So V prime is going to be located at 8, -10. So 8, -10 would then be V prime. Now I'm going to go ahead and use a straight edge here to make this nice and neat so that we can see something also with our dilation, since this is the first one I'm constructing. All right, we had a scale factor of 2. So it should look like our shapes, basically twice the size. Okay, but really the distance from center is twice as much. Okay, the center of my graph is located at the origin here. So if I connected corresponding vertices with the center of dilation, or the origin, they should line up. And you can see here, okay, that W and W prime, okay, line up with the center of dilation, okay, or even Z with Z prime. Okay, and that would continue to any of your vertices that you would line up. Okay, but if you kind of compare that to its original part. So as long as your center of dilation is the origin on your graph, you can use your coordinates and just multiply them by your scale factor. Distribute that scale factor to each coordinate to find the coordinates of your image when you're graphing that out. Okay, that stays the case, okay, even if your scale factor is a fraction. So this time, okay, K was equal to 1/2. So that should make this one a reduction. So I just want you to kind of look at how that would look. I'm not going to do all the coordinates here, but I'm going to get you a start. Okay, point P was located at -6, 2. P prime would then be multiplied by that scale factor. So half of -6 is -3. Half of 2 is 1. So then at -3, 1, we would have P prime. And then you could see that, yes, that would line up with the origin, okay, on my graph. Okay, and it's half the distance the original was from that center. Okay, you should, if you plot out your other vertices, you should get a similar, okay, polygon there when graphing that. All right, it's your turn now to kind of work with your assignment on dilations. As you work with your assignments on the Google Forms this week, please make sure to work the problems out on a separate sheet of paper, preferably graph paper if you have to graph some of these, and then match it up to your choices. It's much better if you work these out on your own, okay, and then select your answer within the Google form. Okay, just a helpful hint for you. All right, good luck.